So welcome back to the lecture of biological wastewater treatment. Now we want to continue with system analysis and kinetics in biological wastewater treatment. I will disappear and we will have a look to the kinetics. We have talked in the last video about the enzyme kinetics, and now we will go to the kinetics of activated sludge. Also finally the idea in behind is that one of the many enzyme catalyzed reactions is a bottleneck reaction, and therefore the final overall reaction should be in the same structure. Now this was proposed from Monod, and therefore the kinetics is called Monod. Another thing that we are doing, that the growth of microorganisms is directly combined with the uptake of substrates. This we will see. If you are from the biotechnologist side, you will see there are other forms of growth as well. But this is a predominant form in the wastewater treatment. Yes, and therefore the growth rate is formulated in this Monod type form, which is adapted from the Michaelis-Menten kinetic. This is called monokinetics. Yes, and we have learned also in the enzyme kinetics that sometimes there are different substrates are required, especially if there is an oxidization process like nitrification. If there is no oxygen, no reaction takes place. And then this is sketched with a Monod double substrate kinetic. In general, normally all required nutrient could be expressed in the so-called monotherm. This could be triple or something substrate kinetics as well. In many cases, other nutrients are not limited, so that the concentrations are a lot bigger than this saturation coefficient. This is called Ks. And so this term becomes nearly 1. Oxygen is a hardly dissoluble gas, and therefore this is often also limited. And we have here also learned that there may be some inhibition take place. In the wastewater treatment, there is the main focus that for the denitrification process, the concentration of dissolved oxygen is inhibiting. And normally this is expressed with this non-competitive inhibition effect. And there are some other very special things, but this is the main part that is used in the wastewater treatment. Yeah, how to detect these parameters? Also there you can use also this respiration cells and measuring the oxygen uptake. Also here finally this is aerated, and the aeration is switched off and substrate is injected, and then normally what you are observing fast decrease of the concentration of dissolved oxygen, and later on this curve becomes flattened but still constant. Yes, and here is only sketched, this is modulation as a substrate, and here the substrate is almost used. And finally this what you are observing here is the endogenous respiration of the microorganisms. This is what happened with us. We are also heterotrophic organism, and if we are not eating, we are still respirating and losing weight. This is the same here. And finally the oxygen uptake, that is only used for the substrate degradation. We can calculate with this formula, subtracting this slope from this slope, and then we can vary the concentrations and so on and find out what type of kinetics we have, for example. Yes, but finally this is more scientific. We want to make a design of reactors and describing the behavior of systems, and there a very useful tool is mass balances. You can make balances for masses, for numbers of moles, for example, for energy and for impulse. and there you can describe nearly everything in technology. Therefore, this is a quite important tool for us, a method to find solutions and go ahead to analyze processes and find good solutions. What is accumulation? Is the change of mass in the system that we are making the mass balance for due to time. Normally this volume, I put a R for reactor, is the volume where the reaction takes place. This we can remember. This is quite important to focus on this. This makes mass balancing a lot easier. Yes, and finally the change by time is expressed by the devariation of time. Then we have transport. Sometimes we have a transport in and a transport out of concentrations, which are expressed with volume flow multiplied with the concentration that enters the reactor, and maybe others are leaving the system. And so this is a typical transport. But we have other transport phenomena, the transport through the surface of the boundary layers, also for example from gas bubbles for the aeration. This is expressed with the volumetric mass transfer coefficient multiplied with the saturation concentration minus the concentration in the system. And of course multiplied with the reactor volume, because we want to have here the mass transfer, the mass per time. Also finally here are the reactions. Normally this is always mass per time. And then we have reactions. In this case this is the reaction rate multiplied with the reactor volume. Also finally I want also to explain a little bit the nomenclature that I am trying to follow. This comes from the IWA, the International Water Association, for their activated sludge models. Finally, C means the total concentration. And this consists of the concentration of the dissolved components, which I'm using as an S. There you see S, this is the concentration of dissolved oxygen, and X, this is the concentration of particulated components. The sum of both is C. If we are operating, which is quite often the case, with constant volumes, this is mainly the case, not always. If this is not the case, finally we have to use the product rule for devariation. But in many cases the reactor volume is constant, and so we can bring it out from the devariation, and then we are coming to a form like this, which is also widely used. If we are dividing by the reactor volume, then this comes up. Now we want to have a look to typical types of reactor and make a process model of different reactors. Also first we have a look to a batch reactor. That means we have here a reactor which is steered. This is quite important. It means that the concentration in the liquid phase is the same in all places of the reactor. And the volume where we are doing the mass balance for is the liquid volume, where the reaction takes place, also excluding the gas bubbles. And there we are applying the idea, also finally assuming the reactor volume stays constant. Then we can use that the accumulation is equal to the reaction. Besides the oxygen, there is a transport through the boundary layers. But finally, and then this is multiplied with the reaction. And in this case, we have the monokinetics, double substrate monokinetics, the growth rate, multiplied with the biomass concentration. Also we can imagine if the biomass concentration is double the size, we have double the size reaction rate. Also finally, if the concentrations are the same, of course. And we have here a stoichiometric coefficient, also 1 divided by the yield coefficient of the heterotrophic microorganism. This H stands for heterotrophics. And of course the minus, because hopefully we will degrade our substrate. And I'm expressing this with the minus in the mass balance. Yes, for the oxygen we have the same. We have, of course, another stoichiometric coefficient. Also this special form comes that the biomass is also in this case measured as COD. And yeah, finally we have here the same, the substrate uptake. But as you see in the slide about the respiration, we have get notice if there is no substrate, there is still consumption of oxygen. This is here due to the endogenous respiration. And the decay coefficient is expressed in the activated sludge models with B. And of course, this will be very soon empty, the oxygen. We have to transfer oxygen in the system, and this is due to the volumetric mass transfer coefficient multiplied with the gradient, with the saturation concentration on the surface of the bubbles and the concentration inside the liquid. Yes, and the biomass, of course, is growing with the growth rate. And if there is no substrate left, well, parallel also reduced due to endogenous respiration and cell lysis. And if you have a system of differential equations like this, to solve this we need normally initial conditions. For t equals 0 we have initial concentrations of all these components. Yeah, these models are normally presented in so-called process matrices, where the component is in the columns and the processes in the rows. Also here we have also put in autotrophic organisms, also nitrifiers as well. And yeah, here are the growth rates for heterotrophic and for autotrophic microorganisms, the decay rates. Also they are different from heterotrophic and autotrophic. And inside the fields of this matrix there are the stoichiometric coefficients. And in the mass balance the reaction is compiled as a sum of the stoichiometric coefficients multiplied with the growth rates. Also if we want, for example, for SS to do so, then we have this minus 1 divided by YH, and then plus 0 times the decay rate of the microorganism. Or for oxygen, we have here exactly this, what we have seen. And so we can transfer this process matrix easily to mass balance. Yeah, then we need beside our process variables additional values. In this form the initial values. We have also in this case for the batch reactor not, but normally we have to know what is the size of the reactor. We need also other information like the saturation concentration of oxygen. There we can use empirical formulas to calculate the concentration depending on temperature. And also we need ideas about the volumetric mass transfer coefficient. Also finally we have to have a look to suppliers' data sheets, or we have to measure the volumetric mass transfer coefficient by ourselves. But finally batch reactors are really seldom in wastewater treatment. This is mainly in the lab, also to find out whether the components are biodegradable or get some ideas about the kinetics. Normally we have here some more continuous inflow and a continuous outflow. Finally everything is steered as well, and we have a special reactor volume which is the liquid volume of our system where the reaction takes place. Yeah, there we get some more important data to consider. We have to know what is the inflow, and we need also the inflow concentrations of our components, of course. Yeah, the rest is the same. And the differential equation changes only slightly in this case. We only have to add the transport term, the convective transport term for the substrate, the oxygen and the biomass. In this case, the inflow is the same as the outflow. So finally, the evaporation or production of water is negligible, also very, very small. And yeah, these equations we have for this type of reactor, which is called CSTR, continuous stirred tank reactor. If we analyze this, we will see we would need quite big volumes to do so, but therefore we will do some adaptations. And here for our two types of variables, the heterotrophic and the autotrophic microorganism, is shown what would be the influence of the reactor volume for the concentration in the reactor or in the outflow. And there we see if we have very small reactors, nothing happened. The concentration stays constant, and then suddenly the concentration goes down. But the very interesting thing in this case is, if we, for example, choosing 1000 cubic meter as a reactor volume, we have nearly 99% degradation of the organic biodegradable fraction and no at all degradation of ammonia, also in steady state conditions. Also this is an example for steady state conditions. That means that these ds or dx per dt is 0. Also we call this mathematically stationary conditions. In the wastewater treatment technology, they call this stationary, they call this, I don't know. But finally, this is calculating the mean behavior of the reactor, not the dynamic. Yes, and the biomass is going then up, and for bigger reactor volumes goes down. And finally, we need at least 1900 or something like this cubic meter reactor volume that the autotrophic microorganism can grow. This we will analyze later a little bit deeper. Finally, the fact is we need big reactors, as we see in this case, and this is due to the fact that we are losing with the effluent always our biomass, our catalysts, and we need a more or less higher biomass concentration to have a fast reaction. And therefore we're doing this experiment in mind that we have our CSTR, but we are separating the biomass. Also with the membrane. The membrane has, for example, special issues that they are separating 100% of the biomass, but lets the substrate pass through. Now this is done, for example, with micro or ultrafiltration. And then, of course, we have to remove excess sludge as well. But there we are using a smaller amount. And there we have control about the sludge removal rate. The concentration of S is here the same as after the membrane, because this is not changed. And the sum of Q out and Qxs should be Q in as well. And for this we are doing the mass balance as well. And there we see we have the same. Also this is because Q in is Q out and Qas, and therefore this transport term is not changing for the dissolved components. For the particulate, this components, this is quite different. There we have now this approach. Also finally this would be QES divided by VR, also because this reduced volume flow that goes out. And this reflects with the sludge retention time, where we will talk as well very soon a little bit more, because this is a very important design parameter for wastewater treatment plants. Yes. And here we are making one example with the excess sludge flow. In this case, if we have a very low excess sludge flow, then we have quite high concentrations of microorganisms. Also finally here the S, the dissolved, is yeah always 0. You will not see this. The ammonia finally is coming up later on if we are increasing the excess sludge flow rate over 290. Then we see that the ammonia concentration goes out completely and the head autotrophic microorganisms are disappearing. They are washed out. So this is to analyze. But now we want to come to the sludge retention time, which is a very important measure. So finally, the sludge retention time is the biomass in the reactive system, also in our reactor, where the reaction takes place with respect to the sludge removal mass flow. Also this is in kilograms per day, and this is finally kilograms, and finally there's coming out a time, also the sludge retention time. Yeah, for the CSTR with biomass separation, as we have, there is the biomass in the reactive system, this is the reactor volume multiplied with the concentration. And in this case we are removing the sludge as well directly from our reactor. This is QES multiplied with QR. And therefore we see that QES divided by what the reactor volume is 1 divided by the sludge retention time, which was here in the mass balance. Yeah, for an activated sludge system, there we have here a clarifier for the separation of sludge. The sludge retention time is compiled from this formula. For a stationary system or static system, the sludge amount in the reactive system is the same, the mass, but the sludge is removed in the outflow because the clarifier will not separate 100% of the biomass. There are still some grams per cubic meter in the outflow, and of course the excess sludge that we are removing. But these are other concentrations that we don't know yet. Yeah, now we are doing a sketch of our activated sludge process in the easiest form. There we have our reactor, and the outflow of the reactor goes to the clarifier. Finally the thickened sludge is brought back, one part, but there is still some part that is rejected as excess sludge. And of course we have an outflow. And if we are seeing a system like this, we have here different options to put the boundaries for our mass balancing. Also we can make balances for our system 1, which we are putting around the reactor. We can make mass balances around system 2, which is only reflecting the clarifier. This has the advantage that there no reaction takes place, and we can make a system overall. And then we will see what comes out. Also finally we are now considering stationary, also mean conditions, or static conditions. In this case we are assuming enough oxygen so that we can make it a little bit simpler. And also we are assuming that there is no biomass in the influent, which is also not 100% true, but the biomass concentration is really low. And then we have for our system 1, our reactor, the inflow and outflow. Also you would think there is a return sludge flow, but finally the concentration in the return sludge is as well as S and goes in and out. Therefore we don't have to consider this here, but you can think at home. And we have the reaction rate, also the growth rate divided by the yield coefficient multiplied by X, and the reactor volume. And for the biomass, of course, the return sludge with the return sludge concentrations enter the reactor, and finally this goes out. We have the growth rate of the microorganism. Also finally this flow is bigger than this flow, and the decay coefficient. Yeah, we have the system 2. Now there is here finally something going in, and the rest goes out. And finally this should be the same, and for the X component this is the same. There is no reaction. And for the system 3, we have only Q in and Q out, which is maybe different, and QES out. Also this could be the same as here, because QES plus Q out is here Q in, but not 100%, because we have here also the return sludge. But this does not sum up. But this is leaving the system, and we have, of course, the reaction term. Finally, I see there is an error. No, this is here also removed. Also there is this plus must be a minus. I will change this. Yeah? And we have for our biomass balance, there is the growth of microorganism, there's the decay of microorganism, and then we have to remove sludge in form of excess sludge, and we are losing sludge in form of the output. And now we are using the definition for the sludge retention time. And there we see that we can express X out Q times Q out plus QXS times XCS as the concentration in the reactor divided by the sludge retention time. Yeah. So, there are many ways, and if we are consuming this in this equation, then we see that we can eliminate X and the reactor volume, and this leads to this nice definition. Also this is normally for stationary conditions the biomass mass balance for activated sludge systems. And you will always end up to this mass balance, even so if you are combining the system 1 and system 2. Also finally you can do so and use the definition of the sludge retention time. And this applies for everything, also for other systems as well. Maybe the definition of the sludge retention time differs from case to case, but finally for the biomass balance you are always ending in this form. And this is quite interesting to analyze this. Finally we know that mu in this case, where the oxygen concentration is high enough or constant, we can express mu with this monokinetics approach, and then we have the relation between the sludge retention time and the substrate concentration in the effluent. Also finally we want to have this as a low value, and I can calculate what is the required sludge retention time. But in this case we are solving to the substrate concentration. Also finally we are bringing the speed to the other side and then making the reversal of this, and then finally we have this case coming up that the substrate concentration depends on Ks. If Ks is bigger, this might be bigger. And finally, if Mmax is big, this is smaller. Is the sludge retention time. Also we are assuming that the maximum growth rate is a lot bigger than the decay coefficient. And then we see that with a bigger sludge retention time, hopefully the substrate concentration is also smaller. And what we see is a broken rational function. And we see that there the sludge retention time could be chosen, that this becomes 0. This is quite strange. Also finally that there would be some point of a positive sludge retention time where this becomes 0, and finally the concentration infinitive, but the concentration could never exceed the inflow concentration. Also there is no production of biodegradable substrate. And so we can calculate the critical concentration, compiling, thus putting Sin inside this. And finally we are coming to this approach. From this concentration, sludge retention time on, there is a degradation. And if we have high inflow concentrations, that the inflow is a lot bigger than the Ks, the minimum concentration is reflected 1 divided by Mmax minus B. And finally, if you know that the sludge retention time is smaller than this expression, then you know there will not be degradation. So finally, this is here sketched for these values. Also for very small sludge retention times, finally there are staying the inflow concentration, finally the microorganisms are washed out, they have not enough time to duplicate themselves and grow, and if the sludge retention time goes over this critical value of 0.6 days, then the sludge concentration, the substrate concentration decreases very dramatically. And for bigger sludge retention times, there finally the increase is very poor. Also this is quite typical behavior of biokinetics. Yeah, thanks a lot. We will continue in making the science of this within the next lecture.